Hello and welcome to today's webinar, Meshing Solutions in 3DEC. Thank you for taking time out and being here today. I'm Véronica Royot from Itasca France. Our today's presenter is Rima Ghazal. Rima is a senior geotechnical engineer in Itasca France for more than 5 years. If you have any questions during the presentation, please type them into the question box in your GoToWebinar control panel. It's on the right-hand side of your screen. I'll bring them up at the end of the webinar. And if you miss anything, don't worry. We'll be sending around the recording when it's available. And it will also be available on our website. Rima, are you ready to start?
Yes, I'm ready.
Good.
So hello, everyone. I'm happy to present for you today our webinar about meshing solutions in 3DEC 7.0. So to start, we have different meshing solutions in 3DEC. It can be sometimes confusing, and so the objective of this webinar is to put our ideas in the right place and try to inform you, better inform you about the different meshing solutions. So on the left, I have put some figures about meshing solutions using an exterior software to 3DEC. For example, we can do the meshing entirely in 3DEC, import it in 3DEC, and entirely outside of 3DEC, sorry. For example, with Gradle, and import the meshing in 3DEC in the form of either deformable blocks or rigid blocks. Another solution is to do the meshing entirely inside 3DEC. So this is possible with 3DEC 7.0 because we can generate the meshing using geometries. So we can do deformable blocks using geometry or rigid blocks. We can also use geometries to do masonry models or generate a model that conforms to a topography surface. And for deformable models, we have a new interesting meshing command. So today we will focus rather on the solutions that meshing solutions inside 3DEC 7.0. So I will present these different options and will comment about the applications of each option. So we start now by talking about generating a block model from a closed geometry. For example, we can do the geometry, define a geometry in a CAD software, for example, Rhino here, then save it as a STL or DXF, in STL or DXF format, and then we can import it in 3DEC. So here on the right, I see geometry in 3DEC. This is not a 3DEC block model, but only a geometry. And this meshing, comes from the geometry from the DXF or STL file. The second step in 3DEC is to generate the blocks inside this geometry using this command block generate from geometry. So it's one single command that allows us to generate the model. When I use the merge command, I have a deformable model. If I don't use the merge command, we have rigid blocks inside this tunnel. Then afterwards, we have different possibilities. We can join these blocks, add some fractures, add an opening, and then mesh it again to have a deformable model. So when I say mesh it, it's the block command, it's the command block zone generate or block zone generate new to make the block model deformable. We can do pretty complex model models using this command. If we define, for example, on the left, we have defined this model with tunnels, fractures, an inclined surface inside CAD. And then we imported in 3DEC, and with a single command, we can generate blocks, and using merge, we can generate meshing. So we have a global control of the meshing of this model. With a minimum, we can precise the minimum edge and the maximum edge length. And using this command, we cannot precise specifically at specific points in the model the meshing sizes. Another option is to make bonded block models. So models made of assembly of blocks. For example, in this case also we generated geometry either in 3DEC or imported from a CAD software. Here I have generated it inside 3DEC with the geometry generate command for a cylinder or a cube. Once again, this is not 3DEC blocks, but only geometry. And then we can generate blocks inside these geometries, either tetrahedra, or we can do also Voronoi blocks. So this can serve to do some compression tests on these specimens to study block fragmentation or, for example, fracture propagation. Then for masonry models, we can also use geometries. In this case, in a CAD software, we define the blocks. So we have different polyhedra for this model. We save it this time in VRML format, and then in 3DEC, with a single command, we transform those geometries into a 3DEC block model. This is another example with vaults. Then now I'm going to talk about how to make a model that conforms to a topography. So we have two options, either what I showed you first, block generation inside geometry. We can also do an operation which is similar to extrusion, which I'm going to show you now. So the procedure consists of generating this topography. So this is a topography that comes from Rhino or another CAD software. In this case, we define it in 3DEC we import it as a geometry. So geometry with the command geometry import. We generate a first layer of blocks, and then with a single command, we are going to extrude the upper surface of this block layer, and we will generate blocks until reaching this topography surface. So you see this command. We have a number of block layers that we can later join, because we don't want to have in this model different blocks. We can join them in order to suppress somehow the virtual joints. So if I'm going to complete, here I give an example how to complete this model. We can add an inferior block, join everything. We can also add a tunnel, cut the model with a tunnel, for example. Add fractures with the discrete fracture network option in 3DEC. And then make blocks deformable by meshing with the command generate zone. This is an example of what we obtain. And then now I'm going to talk about the option of, so we have seen here that we have cut with fractures or with a cylinder, but we can also cut a block model with a geometry. In this case, we have imported a geometry ellipsoid from a CAD software. We create a box in 3D, and then we will cut this box with this geometry. So we will have some joints forming all around this geometry to be able to cut a block in the form of an ellipsoid. So we'll have inside the model some joints that we don't want them to be here, so we will have to join with the command block join afterwards. Now, if you have generated blocks, rigid blocks, and we want to have a deformable model, we can use two different commands in 3D. So the old command that still exists in the actual 3D is the block zone generate, and the new one is the block zone generate new. The difference between, there are some differences between these two commands. With the first one, we can have a uniform size of meshes inside one single block. So if I want to have progressively increasing mesh size from the left to the right, I'm obliged to cut this block into 4 different blocks or more or less, as it depends on the problem. And inside each block, I will do a uniform mesh. With this new command, we can do this more properly because we can have a mesh gradation inside a single block. So here, what we do is we generate this. We do a brick simply. We define mesh sizes on this surface on the left, and also a mesh size, a larger mesh size on the right. So on the left, I have put 0.5, and on the right, 2.5. And then we write this command block zone generate new with precising the minimum edge, maximum edge, and a factor for gradation, for surface gradation. And we can see that we have a progressively increasing meshing size without needing to cut the block into several sub-blocks. We can also define meshing size in a point. For example, on the left, I have put it in the middle of a fracture, so this can be this can be used, for example, in 3D models where we want to model injection of fluid inside a fracture. We can also specify meshing size on a point on the corner or on the edge or inside a block. So this can be done with the block zone size isolated point command. So here I come to the conclusions. Today we have seen the meshing solutions inside 3D, mainly using the geometries. With the geometries, we can do several stuff in 3D. We can mesh rigid blocks. We can mesh, generate block assemblies inside a closed geometry. We can also generate a masonry model, a brick model. We can use geometries to cut, and also we can extrude blocks to be able to have a model that conforms to a topography. with this geometries, we can also using the merge option have directly deformable blocks. And we have also this new meshing command that allows us to have more control on the mesh size in different locations of the model. So if I want to synthesize all of this, we have different commands to generate blocks in 3DEC. We have seen quite few commands that allows us to have rigid blocks from with block generate, from topography, from VRML, from geometry, and also cutting with geometry. So here you have these different commands. This allows us to be able to have bonded block models, for example, masonry models. We can also have rigid, quite complex rigid block models that we can later on join and do other manipulation, cut the blocks and add the FN on top of it. We can have on the other side models that are, so I'm looking at the right column, deformable blocks that are generated directly from geometry. So in this case, we can use the block generate from geometry command with merge on. With this command, we should have the fractures already existing in the geometry, because when we will have as an output the meshing, so we cannot add fractures afterwards. Fractures and openings should be already defined inside the geometry. This is an option that is suitable for when we have few fractures inside the model, and we don't really have a large control on the meshing size using this command, but we have global control of the meshing. And also with this command, we can have concave blocks and curved surfaces. And then the third option is deformable blocks, not directly from this command, but as a second step after generating the rigid blocks. So this can be done with block zone generate or block zone generate new, which allows us to have a local and global control of the meshing. And so with this option, once we have generated rigid blocks, we can add complex DF and add openings and add more complexity of the to the model, and then mesh it at the end with precise control of the meshing sizes and in location that interests us. So that's all for today. We are open for questions now.
Thank you, Rima. Thank you, Rima. We will go ahead and take some time for questions now. So we received several questions. We have a question from Cataline who asks, can I subdivide a concave block into deformable zones? Is there any restrictions against concave discrete elements? She wants to know if she can subdivide a concave block into deformable zones.
I think that, so I'm not completely sure, but I think that we should have, if we are dealing with the rigid blocks, we should divide concave blocks in order to have convex blocks and then mesh it.
Also,
I'm not sure to understand the question. So If the person wants to have more detailed discussion about this, we can can write an email and yeah.
Yes, I will give your email address at the end of the presentation. Another question, can we import the mesh from the other softwares?
Yes, absolutely.
Yes.
Yeah, we can import a mesh from Gradle. This is what Itasca uses, but we can also use other meshing softwares. The important thing is to have a meshing file that conforms with the format that is accepted in 3DEC.
Okay, we have also Dung who wanted to know what do you mean by rigid and deformable blocks?
Okay, I will go back to the initial slide. So when we talk about rigid blocks, these are blocks that cannot deform inside the blocks. So the matrix is rigid, and the only displacement that can occur is on the interfaces between blocks. And deformable blocks are blocks that can deform.
And
so we have the two options in 3DEC. In 3DEC, we have the two options, and yeah, what I presented today is generating rigid blocks, but then we have to use this block zone generate command to mesh the block. If it is not meshed or zoned, we cannot have the block is still rigid, so we have to have some meshing inside a block in order to make it deformable.
okay, and we have so many questions, and maybe a last one because we don't have time for more questions. Which is the main advantage of importing meshes from VRML format? The main advantage.
The main advantage, so it's really applicable for the main application is for brick modeling. So when we import the mesh from VRML, the blocks that we will have are exactly the same as the blocks that were defined in our CAD software. So the main advantage is if we already have the brick model somewhere else in another software, we can import it directly in 3DEC without needing to do more manipulations to have the brick model inside 3DEC.
Okay. Thank you, Rima. Thank you very much for your attention. For information, we will post the video of the webinar on our website in the following days, and we will send a link to anyone who registered. If you have questions, other questions, suggestions on this presentation, you can contact me at software@itasca.fr, or you can contact Rima Ghazal. Thanks again for joining us today, and we will see you next time.
Thanks, everyone. See you soon.